I would like to welcome Amir AghaKouchak, who is to the podcast. Amir is a professor of hydrology and water resources at the University of California at Irvine. And his research covers many different topics. And today, I think we're going to focus a lot of the discussion on hazards, drought, floods, snow droughts, and fire and things like that. And so thank you so much, Amir, for joining me.
Thank you, Bridget. Good to be with you.
So, Amir, I think in a lot of people's minds, the recent LA fires that just occurred in January, and you don't live too far away from them. So devastating fires, maybe 16,000 properties I saw estimated on the web, $30 billion damage. In different regions, Palisades, Eaton, Altadena. And so I was out there recently for a NASA meeting and, met people who had lost their homes and then drove through some of those areas. So really devastating. Maybe you can describe a little bit, and you had discussed these types of things because we've seen them before in your papers. So maybe you could describe a little bit about them and what you felt like was the lead up.
Sure. Fires can have many different drivers, and maybe look at this specific event. Looking at October to December rainfall, we had very, very little rainfall. In fact, lowest on our historical record during this period. So we had a dry period, and at the same time, we had very strong Santa Ana winds. Santa Ana winds are like very dry but strong winds that set the stage for fires. And the year before, we had a lot of rain. Rain means vegetation growth, and vegetation growth means fuel for future fires. So we had many different potential contributing factors: fuel, dry conditions, and also Santa Ana winds all together. And the winds were very, very strong. So the case of LA fires was really a wind-driven urban fire that was very hard to control, of course, and had significant impacts. So it's hard to say highlight one driver. Usually there are many different drivers that interact with each other and lead to an extreme fire like that.
You've seen this before in different fires. I guess the Thomas Fire in Ventura and Santa Barbara that occurred in 2018, and maybe similar lead-up conditions. Maybe you can describe that a little bit, Amir.
Exactly. So if you look at that specific event, we had a 5-year drought that ended with a lot of rain in 2017, early 2017, a rainy season. And again, a lot of rain means vegetation growth, but that summer of 2017 was very hot and dry. We had multiple heat waves that year. So all this vegetation now dries up and ready for the next ignition. And that year, 2017, in December, traditionally outside our typical fire season, there was this massive fire, the Thomas Fire. At the time, it was the most extreme, the largest fire on record. We have broken that record 6 times since then. But at the time, it was the largest fire on our record. And just 1 month after the fire in December, in January 2018, near Santa Barbara, there was this rain over burned area that caused debris flow event, and unfortunately 23 people died. So this is an example of cascading hazards from drought to a lot of rain and local flooding to, again, drought and heat wave and fire and debris flow events all happening over maybe 5 or 6 years.
And so normally when we think of droughts and floods and these hazards, extreme climate hazards, we think of them in isolation, and we develop indices and look at different parameters like rainfall and temperature and that sort of thing. But what you're describing then is a sequence of events and then cascading hazards that can amplify the impacts. So, you mentioned the 2012 through 2016 drought, which is very extreme drought. And during that period, California developed the Sustainable Groundwater Management Act. But then at the end of that, then you had families of atmospheric rivers coming in January 2017. And then a lot of vegetation growth in response, then followed by drought again. And then, I don't really know much about the Santa Ana winds. Were the Santa Ana winds any contributor at all in the Thomas fire? Or
Yes.
Okay. And do they occur every year? Or
every year the intensity varies, of course, and the timing also varies. Sometimes they happen earlier in the season, and if they happen when vegetation is kind of wet, usually the impact is lower. But then if they happen later in the season when vegetation is primarily dry, and they potentially have the kind of more impact. So the timing varies, the severity, the wind speed varies, but again, they happen every year.
Right. And so, I think probably a lot of people are asking, insurance companies are asking cities and homeowners, what can they do to reduce, what can we do to manage these impacts and to reduce the impacts and to become more resilient to fire and drought and things like that?
Well, I'm not an expert on the insurance side, but we need to work on enhancing our resilience. And if you look at our data in historical events, we see this pattern of extreme rain events, and then maybe a year or two after, large, massive fires. This means that when we see the signal of lots of rain, maybe one or two rainy season, we have to prepare. We have to step up our activities on removing brush and fuel from near urban areas, at least, to reduce the amount of fuel available for future fires. Yes, we don't have good models for fire prediction. Models that predict fire are very, very uncertain. But again, when we see the signal, especially in places like California, that historically we know after a lot of rain, we'll eventually have some large fires. That gives us good lead time for cleanup efforts, at least. But we also have environmental regulations that make it a little difficult in some places. If you want to remove brush or do cleaning, you have to go through a process to get permit, and that process is not straightforward. So we deal with a little bit of overregulation. And of course, we all want to protect the environment. We have environmental regulations for certain reasons. But my feeling is that we are probably overregulated, and it makes it very difficult to quickly respond to signals that we see. So that's one potential issue. So we need to really look back at all of our environmental rules and look at them holistically and see which one makes sense, which ones we need to update and adjust, so we have the flexibility to respond quickly to signals that we observe. And also, when you look at urban fires, it's pretty obvious that materials play a big role. And looking at building codes, we have seen improvements over the years on fire-resistant materials, but we need to do a lot of work in this space, working on materials that can improve fire resistance and create incentives. This could be insurance incentives or tax incentives to upgrade and improve local resilience. Especially, this is really important in urban fires.
Right. And then also, I guess, the wildland-urban interface, with the increasing urbanization and expansion into outside of our typical urban areas, then there's increased vulnerability associated with that. And even somebody was saying to me, an emergency manager was saying, well, you shouldn't have a wooden deck, and of course we do at home. Right. and I'm sure it's not fire-resistant wood or anything. So, mm-hmm. And then having a certain space between your house and the trees, and as you say, the difficulty of cleaning up. So you have millions of dead trees from previous fires or droughts or whatever, and and who's going to clean up these things, especially in these open spaces that, who is responsible, and it's expensive. And so there are a lot of things that, we might be reluctant to do or pay for, whatever. But as we keep seeing these fires, then maybe we will get better at and take heed of these things.
I hope so. I hope we learn from all these devastating events that we need to update and adjust and improve. And historically, we have. If you look at flood risk management, if you look at drought risk management, over the years, we have made significant advances. Fewer people are dying now from floods than 50 years ago, 100 years ago. We know that. That's data. Because of everything that we did, fires in the scale that we see today are relatively new. Of course, we have always had fires, right? I'm not saying we never had fire. We had fires, but in terms of impacts and frequency and severity of events that are happening, they're relatively new. And we need to work on solutions, just like what we did for floods and many other extreme events.
Right. And so, life is risk management, and you think about the hazards, which would be, the drought, the floods, or the fires, and then your exposure, and then your vulnerability to those. So thinking of all those components of a typical risk management. And one of the things that you mentioned when we chatted the other day was that we really don't have the data together to address these compound or cascading events. And so what are your ideas about trying to pull those data together so that we can have them for operations or other things?
Right. But you mentioned earlier in our conversation that we usually look at these hazards separately, and that's correct. If you look at individual hazards, there are even different agencies in charge of different extreme events or hazards. Like we have NOAA that mainly is in charge of atmospheric extremes, and USDA is the main federal agency that works on fires. And also USGS maintains our flood records. NOAA maintains our rainfall and temperature data and other atmospheric variables. So from this perspective, and also they have, like, NOAA has warning systems for drought, for storms or extreme storms, but they don't provide the same kind of fire simulations, for example, or fire warnings. Only fire weather, not actual fires. So from that perspective, ideally, I think we need to move toward integrated systems. So not just from the science perspective, but also operation agencies. It's maybe it's a hard thing to do, but eventually we need to converge on kind of unified system for all these different hazards, because they are related. Yes, they happen over different time scales, over different spatial scales, but they are one way or another related. And ideally, we want to look at them holistically, even at the warnings level. And then scientifically, you're right. When you look at research in this space, most papers, most studies focus on one hazard at a time. The compound events are getting more and more attention. Now we know extreme events interact, and we need to work on methodological methods for risk assessment. A lot of our existing guidelines and methods are based on one hazard at the time. So, and there are even specific cases that we know they are related, and we have even models that we can use to model compound events. But when it comes to guidelines, we ignore those relationships. For example, when you look at USGS flood frequency curves, the way the flood frequency curves are calculated in coastal areas, they ignore the dynamics of ocean water level, high tide versus low tide. But we have hydrodynamic models. We can simulate numerically with physics-based models the interaction between ocean and river, right? We have the tools. But when it comes to guidelines, like estimating your 100-year coastal flood, we ignore this ocean dynamics, right? So one of the studies we worked on, and now it's part of ASC Manual of Practice, is a framework that allows you to bring ocean and river data together for multi-hazard flood risk assessment in coastal areas. So both on research and operation spaces, we have this disconnect between different hazards, and we need to work on both dimensions.
Right. And I think we're starting to do that. I mean, we are working on a project for the Department of Energy on hurricanes and recognizing storm surge and inland flooding and pluvial flooding, and trying to put it together then to understand the overall risk. So I think we're moving in that direction. And but we have a lot more data now. We've got detailed, you mentioned debris flows and stuff like that. We've got detailed topographic data, LiDAR data, and other and remote sensing and airborne and drones and all sorts of things. And then we have tools to harmonize these. We have data-driven models or reduced order models to make it faster. But we're still not there at all. We have a long ways to go, but we're moving.
Exactly. Like pluvial, you mentioned pluvial. That's a very good example. We know it's important. We have seen Hurricane Harvey, multiple days of direct rainfall on top of an already flooded area. It's important, but when it comes to guidelines, again, we ignore it just for simplicity, maybe. But now we know that we should change our perspective and maybe account for these seemingly little things here and there, but overall, this pluvial over a major event like Hurricane Harvey plays a big role.
One of the things that you mentioned is, a lot of our hazard indices and everything, drought, floods, whatever, focus on the drivers. And we really don't have indices that consider the impacts.
That's correct.
And I know that's going to be challenging, but maybe you can describe that a little bit, Amir.
Exactly. So if you look at, for example, current drought monitoring or assessment systems, they show, for example, rainfall deficit relative to long-term record, or soil moisture deficit relative to, some kind of baseline. So they focus on variables or drivers mainly. And there is this disconnect with impacts. Impacts, I mean, for example, impact on crop yield, the agricultural sector broadly, or impact on water availability, impact on in terms of storage in our reservoir systems, water supply. And because of that, it's really hard to link what we see from our existing drought monitoring systems with decisions. For decisions, you need to have an idea about impacts. And we call this a perspective impact-based monitoring. So we need to move toward impact-based monitoring of extreme events, including droughts, floods, and so forth. In other words, if this online monitoring system is showing deficit in certain variable, let's say rainfall, this should be linked to impact on maybe food production or maybe jobs, unemployment, or something that can translate the kind of climatological deficit into societal impact, socioeconomic impact. That allows us to make better decisions if you have an idea about impact. It's not easy, it requires a lot of data, but now with data that we have, as you said, we have now a lot more data than 20 years ago, 50 years ago. I think there are opportunities to move toward this direction. There are studies already published in impact-based drought monitoring, flood monitoring. So we need to put more effort, I think, in operationalizing this sort of impact-based systems. The other dimension of impact-based monitoring of extremes is this notion of trade system, trade networks. Impacts can propagate across space. So a drought in the US will not result in food deficit or calorie deficit in the US. Impact will propagate to countries that import food from us, just because we produce so much food, right? And most of it goes for export, right? So this kind of propagation of impact is something that today we can model. We have trade data, we have network models, so we can simulate how local droughts will propagate around the world. And we can potentially look into compounding effects of drought in different continents. What if there is a major drought in the US and at the same time there is a major drought in Australia, two major food producing countries? Again, these events may be climatologically independent, but they can have major compounding impact on each other when it comes to global food distribution or food trade network, and cause significant deficit of calories in another part of the world that has nothing to do with Australia and the US.
I think I've seen some papers like that a few years ago, where they looked at climate teleconnections like El Nino and then drought here in one country and another country, and then which countries were totally reliant on those or who had a diverse portfolio that they imported from. And so I think you also mentioned in some of your papers like this shock, translating shocks that the economists do and stuff like that. Mm-hmm. So I think we can learn from those and start to do more of that and better understand our vulnerability then, considering just direct vulnerability, but also based on our trade and other aspects.
Absolutely. In this space, what I am personally interested in is compounding effects of climatic and non-climatic events. For example, the war in Ukraine, we know, has caused a lot of problems for countries that imported food from Ukraine. Ukraine is also a major food producing country. For example, Egypt import foods from multiple countries, including the US and Ukraine. What if there is a major drought in the US and war in Ukraine? Or different combinations of extreme events and non-extreme, completely independent non-extreme events. The issue with with independent events is that we cannot use traditional statistical models to bring them together. Like war and maybe drought in the US are completely independent from each other. But again, we have trade networks, graph theory, and a lot of mathematical models that allows us to look at compounding effects from impact perspective, not from drivers perspective. And those questions are really fascinating to me.
And do you think, coming back to drought indices, like the US Drought Monitor, they don't really consider impacts that much, do they? But after a drought, you'll see reports of, the livestock loss and the food loss and the billions of dollars of damage, but nothing ahead of time, no sort of forecasting. And you also mentioned, it'd be good to do scenario analysis for these hazards, for these compound hazards, and how to help emergency managers and evacuations and all of these different things. So that kind of combined data set and modeling and stuff would help these people also try to manage these events.
I agree. In fact, in most cases, if you're surprised from an event or a series of events, it's too late to do something really significant, right? You don't want to be surprised. And to avoid that kind of surprise of a series of events, compound or cascading events, we need to have a good understanding of all possible potential extremes and combination of events. And one method that we have used in different fields is this kind of models of different kind of shocks to a system, trying many different possibilities and looking at response of the system. Again, we have a lot of developments in this space in economics, finance, models that focus on, like, for example, the financial market, stock market. They kind of run scenarios of what if scenarios of, oil prices going up, or oil prices going up and gold prices going down, and, different conflicts even. What if there is a major war? So we need to do some of that also in our field, looking at combination of different extremes that can potentially lead to massive societal impacts. And to understand those events, we need to develop models that are reliable and then run many, many different scenarios of compounds and cascading events, and basically get an idea about what combination of events can potentially cause massive disruptions, and what's the likelihood of those events to happen together. And specifically, we need to look at even non-climatic independent events, problems that can happen in another continent even, but can potentially affect us through networks and trade networks. When it comes to evacuations, it's the same story. Right now, if you look at fire evacuations, they are based on location. So if fire is happening, emergency managers decide what area to evacuate. And in the recent LA fires, there were reports of people getting stuck in traffic, problems with evacuations. A few years ago, Oroville Dam was in danger and the spillway failed, and authorities tried to evacuate 200,000 people from downstream. And it was not very successful. A lot of people got stuck in traffic. It took longer than they expected. And, for major events, evacuation needs a lot of preparation. And I think for extreme events, again, we need to run many different scenarios in advance and mathematically practice evacuation on paper. Like, if there is an event here, what areas should be evacuated first? If it is in a different site, and through that experiment, develop event-specific evacuation plans. So, for example, for Angeles National Park, on the eastern side, if the fire starts on this side, what areas should be evacuated first and how? And what if the same fire is on the western side, and so forth? Again, it's not easy. It takes a lot of time, resources, and effort, but I think it's needed to have evacuation plans that are event specific.
Right. And, I think Austin is, the city of Austin is ranked 6th after a number of California cities for fire vulnerability. And I think some suburban areas, they only have one way out, and stuff.
Mm.
And so I think if they went through some of these types of analysis, and we're not talking about off the wall scenarios, we're talking about things that we've seen even sort of, and that maybe make it more realistic to go through that first with them, and then, expand, because extreme events are generally low probability, but it can be huge impact. And so I think these exercises would be extremely valuable, and putting them together and mathematically going through it, and working with the emergency managers and all of these types of groups, and bringing the agencies together. You mentioned, USGS is responsible for river flow and floods and stuff, and NOAA is responsible for rainfall and other things. But we even see the same thing in hydrology. One agency is responsible for groundwater, another agency responsible for surface water. But when they pump the groundwater, they reduce the surface water.
Right.
So
that's correct.
So all of these things are interconnected, and because of these interconnections, then the risk may be amplified. And so looking at them solo, just won't get at the true risk.
Mm-hmm. Right. And you mentioned in many places we have only one way out. We have a project right now in Lake County, California, and there are areas that there is only one way out. What if that road is blocked? In fact, I looked into hazard mitigation plans from multiple cities. FEMA provides funding for cities and counties to develop their own hazard mitigation plans. And I went through a bunch of them to see if there is any information, if there's any map on places where they have only one kind of access. I did not find that in maybe 4 or 5 hazard mitigation plans that I looked at. And that is concerning. If we don't know exactly where those places are, and if they are not in our hazard mitigation plans, we have a problem. So it's a major issue, I think.
Right, right. And that's just one of the things to think about, but
Right.
there's so many others. So I think that scenario analysis sounds fantastic. And one of your studies emphasized anthropogenic drought. You know, we're accustomed to thinking about meteorological drought or agricultural hydrologic, but maybe you can describe what you mean by anthropogenic drought.
Sure, absolutely. So you're right. We usually look at deficit in precipitation and soil moisture, but we sometimes ignore local water demand. In many places, our local water demand dominates everything. So, for example, in Southern California, even in a wet year, we still have to bring water from Northern California, from Colorado River to survive, right? So we are, in terms of net water availability, without importing water, we are always negative. It doesn't matter if it's a wet year or dry year, right? So this is an example of kind of anthropogenic drought. We have created this situation, right? There are many other cities or areas that have more or less the same kind of condition. In some places, it's really bad. Lakes are drying, wetlands are disappearing, because again, there is a basically deficit, like a constant deficit. Groundwater levels are dropping because, again, human water use is kind of dominating everything. So that's one kind of dimension, putting emphasis on this human water use, water withdrawal from groundwater systems, water transport from one basin to another. The other dimension, of course, is the climatic part. We know that emissions in the atmosphere can potentially change your rainfall. So there are two aspects, but what I am more interested in is local water management, what we do locally, because that's where we have control. Yes, emissions, we cannot control it immediately. And even if we do, that there are long-term impacts on the atmosphere we don't have much control on. But how much water we are extracting from our groundwater wells, we have control on. How much water we are bringing from different basins. So with that concept, we wanted to put local water management, water demand, and decisions into perspective of the overall water balance. So we call that anthropogenic drought. And if we believe that if this kind of condition continues for a long time and this deficit increases, it can lead to water bankruptcy in a place where it's really hard to recover from that situation.
Right. I think, a little bit of what you're describing is what we're seeing in the High Plains aquifer, in the central and southern High Plains, the over abstracting groundwater and to support irrigation. And the recharge it hasn't been recharged for thousands of years. So I recall a colleague doing a study on climate change impacts there, and they said, well, this is dominated by pumpage.
Mm-hmm. Absolutely.
Is that not controlled by climate? Yeah.
I totally agree. In several study areas, when we looked at climate change and variability and human water use, the human part dominates significantly.
And I think maybe Charlie Borsmotti had a paper in Science in about 2000 where he was looking at population impacts versus climate impacts, and emphasizing the importance of populations. And I think, that puts more control on people and how they want to adapt and how they want to handle the situation. So, transitioning from irrigated to dryland agriculture or changing crops or doing different things then to adapt rather than just saying it's something that's outside my control and I can't do anything. I think it's, maybe they can manage it or they understand what they're doing and this is what they want to do, but it's maybe not sustainable.
Right. And in some countries, at least, politicians use climate change as an excuse. Sometimes they say, oh, there is this drought and this lake is disappearing and groundwater is dropping, but it is because of climate change. We are not responsible. We didn't do anything wrong. And if you look into, a lot of politicians just use it as an excuse.
Right, right. So, I mean, California is moving more towards sustainable management, groundwater management act that passed in the middle of the extreme drought that you were describing, 2012 through 2016. So the act passed in 2014, and now they're developing plans to bottom up then with all these agencies, sustainable groundwater agencies, I think, and then developing the plans and then putting it all together and having the state as a backup if the local groups cannot manage to do this. So that's moving in the right direction. I think it's improving the data availability, groundwater levels, reporting of wells going dry, and all of these things, which is very important to understand.
That's right. I think it's going in the right direction. An extreme drought brought us together for this to happen. So that was the positive side of a major drought. And usually, after a major extreme event, we come together and we try to come up with solutions to improve our resilience. And this is a good example. And as far as I know, it hasn't been a very smooth process. So still some farmers don't like the way things are being managed. And there are all kinds of complaints and lawsuits here and there. But overall, I think it's moving toward a good direction. We needed to do this. And you know this better than I do. It's a long-term plan. Like they started this slowly, phase by phase. And I think that was very smart. They didn't try to change everything overnight. That was very smart of the managers. I think they slowly expanded the scope and the rollout, but kind of over a 10-year process, and then the next 10 years and so forth. And I think overall it's going toward the right direction.
Right. And I think in some of your studies, you describe how we can try to manage water resources more sustainably. Oftentimes we focus on the supply side, increase supplies, desalinate seawater, reusing wastewater, I think is great. Interbasin transfers, different things like that. But then reducing the demand, I think the urban areas are doing that, and incentivizing it with technology and other things. And then storing, the Army Corps of Engineers doing a nice job with the forecast informed reservoir operations and linking surface reservoirs with managed aquifer recharge in LA. So Prado Dam and managed aquifer recharge, that's really nice. So a lot of things are make one hopeful that, with all of these different, and we need to move everything, in the right direction.
I agree. Demand management is really, really important. And we really need to start with demand management. And traditionally, you're right, we focus on supply, bringing more water through water transfer or desalination. But I think demand management should be prioritized. And then looking at supplies and how you can improve your supplies. In major cities, water recycling wastewater is definitely a great opportunity. Here in Southern California, locally, I think they recycle 200,000 gallons per day. And then all the greenery in Southern California, in our area at least, it's all with this recycled water. And it has improved our aquifers here. If you compare in our region, in Orange County, even during the latest drought, water levels in our aquifer systems were healthy just because of all this recycling. So it can have really long-term positive impacts. But yeah, this demand management is really important. And in many other countries, if you see what's happening to lakes and reservoirs drying, and the main problem is, again, the demand is way more than what's available. And without demand management, we'll see significant environmental impacts.
And you have had water markets to a limited extent in California, and that helps, and you also mentioned, trying to go to higher value uses. And I oftentimes think, well, we'll just all be drinking wine and we won't be eating it all. Because the vineyards maybe or whatever would be the higher value.
Right.
But the water
and
markets.
almonds.
And almonds, yeah, a gallon an almond.
Something to eat.
But the water markets, I guess during drought, you can buy, not use your water or things like that, or maybe in the past you would fallow the land, but now more perennial almond trees and other things, so it's much more difficult to fallow land. But in the past, you would fallow land, and near San Antonio in Texas, the city purchases water from the agricultural sector if they know there's going to be a drought, and then they won't use it for irrigation. So these sorts of things, and I mean, even in Phoenix in the Lower Colorado River issues now, but all of those were temporary measures, and they weren't permanent buyouts, from agriculture. But I think long term, we'll just see water moving from agriculture, because it's the elephant in the room, to the other sectors.
Yes. And historically, if you look back, we have seen these transitions from mining sector to agriculture sector, and in many places from agriculture to services or agriculture to tourism. And even in California, things are changing, and agriculture is a very small fraction of GDP in California. Even our most extreme drought will not have that much of an impact on the total GDP, right? But it varies significantly in some other countries or some other states. Not the case. Agriculture is really a big part of the economy. So the shift is happening. Especially in California and many other places, especially in the developed world. And because of that, so yes, there is a shift in balance of water and the value of water as well. And the markets, it's good to have the market, at least it gives you some flexibility to basically between industries, farms and sectors to make the most of available resources.
And I think one of the things that you mentioned in your anthropogenic drought is employment. I mean, we know agriculture is not a huge part of your GDP, but it employs lots of people, and and so from that perspective, I think it's very important.
Yes, absolutely important. In fact, that's why in California there is a lot of investment in this space. It's mainly because of jobs and employment. And we know that unemployment leads to higher crimes and all kinds of long-term health impacts if people lose their health insurance. And so that's the main issue, employment and jobs. Even in California, even though agriculture is a small fraction of GDP, there is a lot of focus on it just because they want to have people jobs and opportunities and livelihood.
Right. So, I mean, in California, then going to the source of the water and to the mountains and the snow, you often see in the news, April 1, what's the snow look like and what has the snow season been? And that's a good predictor of your water availability for the summer. So you've done quite a bit of work on snow droughts and things like that. Maybe you can describe that for California first, and then maybe discuss briefly your global analysis.
Sure. We rely on snow in Sierra Nevada mountains, and snow is like a natural reservoir. We have looked into response of snow to different levels of warming, and we noticed that for a fixed time of the year, let's say April 1st, which is a kind of indicator of a good kind of indicator for snow availability for the rest of the season. It's toward the end, right? Toward the end of the snow season. Even 1 degree temperature change, average temperature change, leads to about 20% change in snow water equivalent at that time of the year, which is very significant. So it shows that even 1 degree temperature change can have significant impacts on snow water equivalent. If snow melts faster than normal, basically flood risk increases early in the season in spring, but we cannot control this water. We have so much reservoir capacity, so we have to let it go to the ocean. So faster snow melt not only increases flood risk, it also increases drought risk, even within the same water year. So it's a major issue, especially with warming temperatures and snow dynamics. This notion of snow drought becomes really important. So a few years ago, we published like a global data set of snow drought to study how they change. We have record of places where we had above average rain, but dry conditions. And when you look at those events specifically, you see the deficit was in snow. Maybe the rain was above average or near average, but because of below average snow, eventually you end up with drought situation.
So the total precipitation was the same, but the snow fraction was lower, and then that made them more drought vulnerable.
Yes, in warmer than usual years, sometimes this ratio of rain relative to snow changes. So you get more rain, less snow. And again, yes, your average total precipitation may be more or less the same, maybe above average. But if it comes in form of rain, it goes out of your system relatively quickly. So ideally, we want it as snow, so it remains in the system longer.
It's just like another reservoir, right? I mean,
exactly.
Mm-hmm. Yeah. And so that shift in the seasonal water availability, so more in the spring, and then you have less buffer then at the end of the summer. And so you're more vulnerable to drought at the end of the summer if the snow. And so your studies then, Northern California, Northern Sierras were more vulnerable to this temperature increase than the Southern Sierras, because I guess the snow is at a higher elevation in the south, about 1 kilometer higher. So in the north, it's about 2.5 kilometers, or
right.
In the
That's
south.
correct. So in Northern California, we get more snow relative to south, and also the snow level is lower. Yes, that's correct.
And so with this temperature increase, then you see the snow at a higher elevation, it just moves up.
Yes, the center of mass basically goes up. And in those papers, we kind of quantify to what extent the center of mass of snow goes to higher elevation because of warming temperatures.
Right. And when you look at that globally, I mean, these high mountain snow areas, they're really the water towers. Right. For a lot of irrigation and food production and stuff. So I guess, with climate change, maybe initially, our glacier melting and things like that, you'll have a higher flow for a certain period of time, but then long term, it would be lower.
That's correct. That's consistent with projections.
Right. A lot of things to think about. So we can't retire yet. Or I can't anyway.
Lots of opportunities and exciting topics for us.
Yes. And a lot of data and a lot of tools and a big need then. So are you pretty optimistic that we will be able to adapt? And as you mentioned earlier, we have advanced a lot in the flood space, in managing flood risk and things like that. And so wildfire, maybe we will get there eventually and keep learning. And I think this compounding and cascading of events, I think the insurance industry is really grappling with that too. And basically cities and all different groups trying to understand how to deal with it. But I like your approach, to try to make ourselves more resilient, to manage the vegetation better after these wet periods, and so that we're not so vulnerable during the next drought.
Mm-hmm. Yeah, I'm an optimist, and I believe we have historically learned from past mistakes, past extreme events, past political problems, and over the years, we have improved our resilience, and I think there are opportunities to enhance our resilience, and we will probably adapt and hopefully survive.
And I like your approach to much more comprehensive hazard indices that include the human aspects that you mentioned, the socioeconomic factors, the employment, and all of these different things, and the impacts on crop production, and I guess even and learn from the economists and stuff, looking at trade networks and shocks and all that, how they transmit. So we'll make countries and other regions more resilient when they better understand these risks. So thank you so much, Amir, for your time. Our guest today is Amir AghaKouchak, and he's a professor at the Department of Hydrology and Water Resources at University of California, Irvine. And
thank you again, Bridget. It was a pleasure.